All right, so let's talk about this. So let's do. So let's simplify this. We're going to do homogeneous linear with constant coefficients. I don't think it doesn't get easier for that for second order. So in this section, we're going to only consider y double prime plus a, y prime plus some by equal to 0, where a and b are less. And in order to do this, we're going to try out a solution of y equal e to the lambda x. We're just going to try the solution. By trying the solution, we find our solutions. Not what I wanted. Still not what I wanted. All right. And so by trying this, let's go ahead and put it in. So what do we, y double prime here would give us lambda squared e to the lambda x plus a lambda e to the lambda x. Because if I took one derivative here, plus b e to the lambda x equal to 0. Here, if I solve this out, I get lambda squared plus a lambda plus b times e to the lambda x equal to 0. Well, can e to the lambda x ever be 0 for any lambda? No, right? It has to be positive. So it's not this. It must mean that this is equal to 0. And so what we do is we call this the characteristic equation. Doggo, you still can't be. Dog, you eat all that food and still hungry? Why are you chewing on me? Anyway, so we get this characteristic equation. And we'll get different solutions based off of what happens here. So if I get lambda, and so I can solve this, and I just want to solve where lambda equals to 0. I might get two different solutions. And if I get two different solutions for lambda, I have one linearly independent solution, two linearly independent solution. Here, if I get the same solution, I'm going to show that in order to get two unique solutions, we'll introduce this x. There's other ways of showing this, but you're going to just kind of take it on faith. And here, if I get complex solutions, I'm going to convert this into cosine and sine. Okay, so let's build each of these in the following section. All right, so let's start with the real distinct groups. I'm going to show you what the answers are. We're going to solve for one, and then we're going to do it. All right, so let's do this. So here, we're going to develop the characteristic equation. So here you make the guess of e to the lambda x. By doing so, you're going to just get, this will just come out, right? You'll just get the characteristic equation out. So you can always just write it down. So the lambda plus 1 lambda minus 2 equal to 0. So here I have lambda, oops, I forgot my squared on my left. Not even writing on the right line. Lambda squared plus lambda minus 2 equal to 0. Any questions on how I got to this? If so, just say sure, and I'll redo it. Sure. Okay, so there's some questions. So here, if I plug this in, if I get double, so y prime is equal to lambda e to the lambda x, and y double prime is equal to lambda squared e to the lambda x. Plugging that in here, I'll get lambda squared e to the lambda squared x plus lambda e to the lambda x minus 2 e to the lambda x equal to 0. E to the lambda x can equal to 0, so this must equal to 0. Okay? So that's where we get the characteristic equation. You just plug in this. We get y prime, y double prime. I want to solve this equation. E to the lambda y cannot equal 0. So lambda squared plus lambda plus 2 must equal to 0. Same reason for this. When I factor it out, this can't equal to 0, so this must equal to 0. So in our case, we have this. So we just solve for what lambda is. Here, this is lambda minus 1, lambda plus 2. So here, lambda is equal, so that implies lambda, lambda 1. I'll just say lambda 1 equals to 1, lambda 2 equals to minus 2. So my general solution in this case is this. Y is equal to C1 e to the lambda 1. Well, lambda 1 in this case is x, so it'd be x plus c2 in this case, lambda 2, which is minus, so e to the minus 2x. And this is my general solution. So here's my general solution. Now, if I was going to solve for the particular, y of 0 is equal to 4 times so 4, hold on. So 4 is equal to, and here I'm just going to take this, and so it'll be c1 e to the 0 plus c2 e to the 0. So this is just, this implies 4 equals c1 plus c2. Here, if I take y prime of 0, this is now minus 5. If I take the derivative of this is still just c1 e to the x, and then I'm going to plug in 0. If I take the derivative here, this is minus 2 c2, right? Because the negative 2 comes out, e to the minus 2x. But e to the minus 2, still e to the 0. So this is just 1. This is just 1. So this implies minus 5 equals c1 minus 2 c2. Now what's this? This is a system of 2 equations and 2 unknowns, right? How do we solve this? Well, all the stuff they teach you in chapter 7. Now, why they wait to teach you in chapter 7? There's a reason I teach this out of order, guys. There's a good reason I teach this out of order. Because all of a sudden, we need systems of equations. Now, could you solve this using other methods? Sure, right? But when we get into the 3x3s, I'm like, why don't we not know how to solve equations before chapter 7? I don't know. So we get this. We just solve it using system of equations. We're going to get c1 equal to 1. We're going to get c2 equal to 3. We can just check that real quick. 1 plus 3 is 4. 1 minus 6 is negative 5, so that works. And so here we have our particular solution of e to the x minus 3 e to the minus 2x. Okay, and that's our particular solution. So the first step, my first step here would be step 1 would be to write the characteristic equation. So that'd be step 1. And get solutions. Step 2 would be to, depending on what you get here. So this is distinct in real, right? So these are 2 different ones in real. We get this. That's step 2. And then step 3 would be to handle any characteristic or any initial value stuff. Okay. All right, and here, if you want, you can graph this answer. I think the book will ask you to graph a couple here. It starts at 4. It kind of goes down and goes up like this. And so that's kind of how the graph looks. If you wanted a graphical representation of the answer. All right, so let's do the next one. Let me take a drink and we'll do the next one. You still hungry, Chow Chow? I'll give you a little more. I know, Snicky's ate all the first one. Here. All right, so let's do the next one. All right, where am I at? Hi. There we go. I said multiple railroads. All right. So let's say we have lambda 1 equals to lambda 2. You don't need this equal sign, sorry. Our real numbers. There's only one solution to this, right? And so we need to find another solution. There are various means of doing this and methods to obtain the other solution is x e to the lambda x, right? Is the second linearly independent solution. There's a lot of ways of doing it. And so you end up with this right here. I'm not going to go over the derivation. I'm just going to show you how to use it for now, and we can do the derivation later. All right, so here, let's just solve this initial value problem. So step 1. So step 1, I'm actually right. Just write out the characteristic. Write out the characteristic. equation. So just write out the characteristic equation. So in this case, it'll be lambda squared plus lambda plus 0. Oops, I said lambda, but I put a square on it for who knows what reason. Plus 0.25 is equal to 0. You just write out the characteristic equation. And how do you get that? Every time you see a prime, that makes a lambda, right? So this is 2 prime, so lambda squared. This is 1, this is lambda, and then nothing. And if you need to, you can always just plug in e to the lambda x, crunch it through, and you'll get this out in the end. But you can just skip right to this. On the homework, on the test, just right to it. So write this. Then we need to solve it. We still need to solve it. So write out the characteristic and solve, right? And solve, right? So let's solve this thing. So if I solve this one out, what do I get? What do I get here? So this is lambda plus 0.5 squared equal to 0. So that means lambda is equal to lambda 1 is equal to lambda 2, which is equal to minus 0.5. Okay. So here we have a double root, right? So multiple real roots. In this case, we only can have at most a double real root. Here we have a double real root. And so step 2, depending on our lambda values, write the corresponding general solution. And I give you all the general solutions. So in some ways, this section is kind of straightforward. You solve a quadratic that you just write from the equation. If it has multiple real roots, use this one. Or if it has different real roots, use this one. If you have multiple real roots, use this one. If it has complex root, we'll do that one next. I think we'll end on that one. We write out a general equation. So here we're just going to write this out. So here I'm going to have EC1 e to the negative 0.5 x plus C2 e to the minus 0, or C2 x e to the minus 0.5 x. And so here's the general solution. And then step 3, use the initial conditions to solve the initial value problem, aka just solve for your coefficients real quick. And so what do we have here? We have this one equal to 3, this one equal to 3.5. So let's go ahead and do that. So here we have y of 0 is equal to 3. And so let's just plug that in. So here I'll get C1 e to the minus 0.5 x, so C1 e to the 0 plus C2 0 e to the 0. Notice this just cancels out, and this just means C1 is equal to 3. That one just falls out directly. And then here we can take the derivative. The derivative is a little bit more hairy. So derivative of 0. Now what are you up to? Oh, I finally fell asleep. Is negative 3.5, so equals minus 3.5. And so what do we have here is we have, so if I took this derivative, C1 still equals C1, right? Hold on, I'm gonna do this real careful. This derivative is minus 0.5 C1, which I know what C1 is, but I'll leave it off for a second. I'll plug it in a second. E to the 0, because I plug in 0 for x, plus, if I take this derivative, I'll have 0, right? Hold on. I'll have x, And then I differentiate this one, so it'll be minus 0.5 e to the 0. I'll plug in a 0 now, so that's 0. Plus, if I do that one, I just get C2 e to the 0. Okay. Everyone see how I just punch through that? So here you have to use chain rule. And so here I have, let me see if I'll have C2. So I'll have minus 3.5 is equal to minus 0.5 C1 plus C2. And that means C2 is equal to, so I plug in a 3 here, I get 1.5. That means C2 is equal to minus 2. There we go. I can do math. And so here I get the final answer, 3e to the negative 0.5x, because that's what minus 2 x e to the minus 0. So here's my general solution, or my particular solution. Okay. So you just have to make sure you use product rule and all that. All right, so we have 10 minutes. So let me do the last one that way, or not the last. I don't think it's the last one. Is that the last thing in this section? No, what's the last page of this section? Oh, I think I start this and then we finish this. Let's see how far we get. Oh, okay. Yeah. We will start this, but we will not finish it. But I do want to get this far. All right, so now let's pretend for 5 seconds. We get complex roots, and I want to convert this into real solutions. And so if we get complex roots, we're going to have the 2 following answers, right? And since it will come this way, since if I have real coefficients, I will have my complex numbers will come as complex conjugates, right? So here I have y equal to the e alpha plus ib times x plus y2 is equal to minus alpha ib times x. Oops, I forgot my e. E to the alpha. There we go. All right. So why not just use this? Why not just say y? So why not just say y equals to c1 e to the alpha plus I beta x plus c2 e to the alpha minus I beta x. Why not just use this, right? Well, here you've taken a real equation and you get this. And so I made this for you guys. It's terrible, but it only took me 2 seconds. Real problems require real solutions. And so we do not want to use, we want real solutions to our real problems. And so in order to do that, we're going to employ Euler's formula. So real solutions are real problems, hold on, require real solutions. Because if you're making something as an engineer, you're going to want a real solution to your real problem. It's like, well, I have this imaginary solution. Your boss comes like, that's great, get out of here, right? So in order to do this, we're going to employ Euler's formula. So Euler's formula yeah, that only took me what, a minute to make in Photoshop. And like these notes would take hours, so I don't feel bad. So we'll have e to the it is equal to cosine of t plus I sine of t. All right, so now let's take one of our solutions. So we're going to take one of our solutions here. And we're going to convert, we'll just take the positive one. We're going to just take e to the alpha, and then alpha, and here I have t, but let's go ahead and switch it back to x. So e to the alpha x, e to the I beta x. So here I'm just distributing in my x, right? Which is equal e to the alpha x times cosine of beta plus I sine of beta x plus I sine beta x. And then we'll go ahead and move some stuff around real quick. So we have e to the alpha x cosine beta x plus I e to the alpha x sine beta x. Okay. And this works. This is a solution. And we call this the real part. And we call this the imaginary part. Imaginary part. Imaginary. All right, so this is real part of the imaginary part. But let me explain something here. So let me just write, notice that if this is a solution, right, is a solution, this is also a solution, right? I didn't do anything to the solution, just change it. But notice that the real part needs to be a solution, and the imaginary part needs to be a solution. And what do I mean by that? If I plug it back to the original equation, I need to get 0 because this part better 0 out, this part better 0 out. And so if this real part, which is real, is a solution, and this imaginary part, and the imaginary part is real. The imaginary part, let me say, I can say that. If I take everything beyond the I, this part, which I call the imaginary part, is real. The part that makes it imaginary is the I stick in front of it. But this is real. This is real. And they're two linearly independent solutions and need to be a solution because they both have to zero out. They both have to zero out. Both have to zero out. Now, basically, they both solve it, right? They both zero out for it to be a solution. But these are real, and I'm going to just write linearly independent. I don't know if you've ever seen this. It's very common, linearly independent for that. And so our solution becomes the following. It becomes, hold on. And so for a complex solution, I guess I don't need to write it down. This is my first solution. This is my second solution. And therefore, the general solution is the following. Okay. So let me explain what I mean it needs to zero out. Let me just show you. Let me go back to this and explain that real quick before. So let's pretend I'm plugging in e to the alpha x cosine beta x plus I sine of x, or I beta sine of, oops. let me back up. Wow, don't do that. E to the alpha x, or I sine of e to the beta x. So let's pretend I have the solution, right? And I know this is a solution. If I plug this into here, this part is always going to remain real, and this part's always going to remain imaginary, right? that means this part is going to solve this equation. And that means this is a solution. This imaginary part better equals 0 as well, because I know that this is a solution, right? And so this part ends up being a solution as well. So this is a solution. And so since this is a solution and this is a solution and they're both real, we're going to use these as my real linearly independent solutions right here. And we just put that in front. Okay. Anyway, so here we have this. So here we just write out the characteristic equation. So this is lambda squared plus 1.4 lambda plus 9.04 equal to 0. If I solve this, you can just crunch this through the 10,000 in 2 different ways. You're going to get minus 1.2 plus or minus 3i. And so here we have the complex one. And so here, using the complex one, so here's step 1. So step 1 was to solve this. Step 2, depending on our solution, we're going to write out a general form. So this is complex. So this is complex. My general complex is the following. C1 e to the minus 0.2x cosine of 3x plus C2 e to the minus 0.2x sine of 3x. And remember here, it'll be e to the real part, cosine to the imaginary part. Okay, or imaginary part times x, and real part times x. So once we have this general form of solution, step 3 is use our initial conditions to solve our initial value problem, I, B, P. Okay. So here we have y of 0 is equal to 0. So 0 equals C1 e to the 0 cosine of 0 plus C2 e to the 0 sine of 0. Well, this is 1, this is 1, this is 1, and this is 0. So this is all equal to C1. This implies that C1 is equal to 0. All right, so then we're going to do y prime of 0 equals to y prime of 0 here is 3. We take this derivative, I'm going to get minus 0.2 C1 e to the 0, because I will say the same. Nope, I think I'm cheating my little face off, aren't I? Hold on. Hold on. What do I have to do here? I have to use product rule, right? Take this derivative. Now, do I need to do product rule for any of this? And the answer here is no, right? Because I know C1's 0. I know it's 0. So I can just instantly say, meh, I don't care, right? So let's do product rule for over here. So here it'll be C2. We're going to keep this one constant, e to the minus 0.2x. And then we'll take the derivative of this, so sine turns into cosine. Plus C2, and then we'll have minus 0.2 e to the 0. I guess I can plug in the 0 now. And then sine of 0. So here I took the product rule and then plugged in 0. And so this becomes 1, this becomes 1. This becomes 0, because that's 0. And so I have C2. So this implies C2 is equal to 3. Hold on. Did I do this right? I did something wrong. Oh no, C1 is 0. So I just threw this away. So I'm using chain rule here. So chain rule or product rule here. So I'm going to take this, I'm going to hold this one constant and then take the derivative of this. I did make a mistake. Where's my mistake, guys? I took the derivative of this. Is it cosine of 0? Or cosine of 3x, which I'm going to plug in as 0? Yeah, but I forgot the 3 because of chain rule. I forgot the 3 because of chain rule. Thank you. Thank you, thank you, thank you. So this implies that C1 is indeed 1, because this ends up being C2. This ends up being 3 equals 3 C2. Okay, so this is 0, so I just throw this away. This ends up being, so I'm only taking the derivative of this. The derivative of this is C2. Hold this one constant. Take the derivative of that. The 3 pops out, which I forgot. And then C2, take the derivative of this one, and then hold this one constant from there. And so there, so C1 equals 1, and then we have our final answer here. Y is equal to e to the minus 0.2x sine of 3 e to the x. And if we kind of graph that, that looks something like this. And this will be important later. All right. Let me just check something. So that's the end of these notes. Just check something super fast. Boop. Nope. No, I want to check. Is that negative? Yeah, it's negative. Hold on. Sorry, let me make this a little bit clearer. This is minus 0.2x. Dang it.